Okay, how are we doing today? Today we are going to begin a discussion with nuclear chemistry. All right, specifically with what radiation and the particles associated with that. All right, first things first, I want to get some background knowledge on you, what radiation is. So that's the bell ringer. So I'm going to stop this for a second, and then I'm going to let this person explain it, and then I will do my job at my explanation after. Okay.
What do smoke detectors, emergency lights, and nuclear power all have in common? Radiation. But what exactly is radiation? Thanks to high school science class, most of us have heard about radiation, but many of us may not know exactly what it is. I'm Julie, and I work for the Canadian Nuclear Safety Commission. Simply put, radiation is the release of energy in the form of moving waves or streams of particles. This energy can be low level, like microwaves and cell phones, or high level, like X-rays or cosmic rays from outer space. These are known as non-ionizing and ionizing radiation. But if we really want to understand radiation, we need to go inside the tiny world of the atom. Remember that high school science class? Atoms are the microscopic building blocks of all matter in the universe. Everything around us is made up of atoms, from the largest galaxies to our own bodies. The center of the atom is called the nucleus. That's where the word nuclear comes from. There is a tremendous amount of energy inside. The nucleus of an atom is made up of two particles, protons, which carry a positive charge, and neutrons, which have no charge. Outside the nucleus are electrons, which carry a negative charge. The attraction of these negative electrons to the positive nucleus is what keeps the atom together. Now, every element in the periodic table has a specific number of protons and neutrons. But sometimes an atom will have too many or too few neutrons. When this happens, it becomes unstable or radioactive. An unstable atom is called a radioisotope. For example, 2 extra neutrons in a hydrogen atom creates the radioisotope tritium. That's the stuff that helps make exit lights glow in the dark. Radioactive atoms want to become stable again, so they release energy until they get back to a balanced state. This process is known as radioactive decay, and there are 3 main types: alpha, beta, and gamma. Alpha particles are heavy and travel small distances. Beta particles are lighter and travel further. And gamma radiation is actually a wave, and it travels the farthest of all. The time it takes for half of the radioactive atoms of a radioisotope to decay is called half-life. Half-lives can range from a fraction of a second to billions of years. Let me give you an example of how half-lives come into play in nuclear medicine. Doctors inject patients with the radioisotope technetium-99m, which emits gamma radiation. A gamma camera can then take pictures of the patient's insides to help with the diagnosis. The relatively short half-life of 6 hours for this radioisotope makes it ideal for these types of tests. Let's pretend these jelly beans are the nuclei of Tech-99m. After 1 half-life, half the atoms still in the body remain unstable or radioactive. After 2 half-lives, 1/4 of the atoms remain radioactive. After 3 half-lives, well, you get the idea. After 24 hours, almost all the radioactivity is gone, thanks to radioactive decay and the body's natural, shall we say, processing? And that ends our science class on radiation. Congratulations, you passed. Now for the book.
Okay, all right, so radiation. It's used in a lot of different ways that people don't necessarily realize. All right, nuclear power. This is a big thing for us in Cicero because we have a nuclear power plant, I think as the crow flies, about 40 miles away. It's used in medicine, both as in imaging and treatment and identification. It's used lots of different ways. Some people don't realize that a lot of food products are irradiated with radiation after they're packed, before they're shipped. The radiation only affects living cells, and it's going to affect living cells by not allowing them to reproduce or to mess up their reproduction. So for a strawberry that's already been picked, so all of its reproduction is done, the radiation that it would be exposed to would do nothing to the strawberry. It's just going to kill any living organism on it. So it makes it have a longer shelf life and makes it last around a little bit longer. All right. So it makes food cheaper in the long run. Smoke detectors, which you should have in your house, as a source of radiation. There are other natural sources of radiation that I will be showing you a video. You'll be watching the video. I'm not going to show it. And you can see all the different places that it comes from. It's kind of cool to see a lot of things people don't realize. Radioactivity was invented by female scientist, Marie Curie. Her life story is pretty interesting. You might want to look her up if you're interested in the history. We're not going to go into it in here. But she invented radioactivity, or discovered radioactivity, I should say, not really invented it. She did lots of things in her life, and most of her work was dealt with radium. I don't know if anybody's seen, there's a movie on Netflix that was just released within the last couple of months called Radium Girls, where there was a radium company in the United States that they used radium because it was radioactive. It glows in the dark. They thought it had medicinal properties where it helped people, and they actually discovered that radium in those dosages was very harmful, and it actually created a lot of work labor issues back in the 1920s-ish. Look up Radium Girls if you got nothing to do. Why is a particular nuclide or isotope stable or unstable? And the lady talked about it in that brief video. It basically has to do with the ratio of protons and neutrons inside the nucleus. All right, nuclear chemistry deals with just the nucleus. All the other chemistry we talk about this year deals with everything outside the nucleus, the electrons. If they're shared, they're transferred, stolen, lost. All right, but this is the one unit that only deals with the particles that are in the nucleus, which are the neutrons and protons. And to make an element stable, it's got to have close to a 1-to-1 ratio of protons and neutrons. All right, the nuclei will break down naturally, and it's called radioactive decay. All right, they're trying to become stable. It's not like that they want to do this, but it's a very predictable decay. So it over the course of time, and that's how we can develop what's called half-lives. You should be kind of familiar with half-lives because you did talk about it in earth science, and we'll revisit it in this unit as well. But the decay is an attempt to correct the ratio of protons and neutrons. All right, sometimes it's a 1-step decay, sometimes it's a 5-step decay. It just depends on what your starting nucleus is. All right, but it's trying to get to what's called a stable nucleus. Once that stable nucleus is reached, all right, it will no longer decay. All right, so it just depends on where you start, how long it takes to get there. This graph is actually a complicated graph. We're going to talk about it very superficially. If you can see, I'm here, like this line and then this extended line right here. This is the band of, it's called the band of stability. It's the 1-to-1 ratio of protons and neutrons. So if you just look at the graph, 40, 40, 50, 50, 60, 60, 70, 70, and so on and so forth. All right, all the elements that are low numbered elements, all right, they generally are very close to a 1-to-1 ratio of protons and neutrons. You can see here the number of protons as you get up into, numbers of 40s. All right, you start to get some divergence from the band of stability. All right, and as they get up even farther, there's even a bigger spread. All right, one thing that you do need to know from this is right here in orange, that any element above number 82, 82 is lead. All right, any element above 82 is, every single isotope is unstable. All right, there's no known stable isotope for any elements that have atomic number 83 or higher. Elements below 82 can be unstable. If you look down here, they can be, these red ones are the unstable ones. They can be unstable, but they don't have to be unstable. There's always at least one stable nucleus. Okay, so that's kind of what we're going to get from here. Yeah, that's it. We don't have to talk about the ratio or anything in here. All right, so a stable nucleus is close to a 1-to-1 ratio of protons to neutrons. All right, the farther it gets away from that 1-to-1 ratio, the more likely it will be unstable. All right, this is a bunch of videos that we normally talk about in class and watch. I'm going to show you one of them. I'm going to push it to you on Classroom. It's pretty cool. A guy goes to the most radioactive places on Earth. It's this one right here in the middle. Okay, types of nuclear particles. All right, you may or may not have heard of these things before. All right, nuclear particles have Greek origin names. All right, so we're going to talk about alpha, betas, positrons, and gammas. It probably would be helpful for you to have your reference tables out. It's table O is our particles that we deal with, and then there's another table of radioisotopes that we'll deal with another day. All right, but there's a notation, and then we're going to talk about strength. And what I mean by strength is what it will go through. or conversely, what stops it is more important, probably is what we want to talk about. So an alpha particles notation is either an alpha symbol, that's kind of, I call it a squished fish, all right? And you could, or a 4/2 HE, or you could write 4/2 alpha as well. Now remember what these numbers mean. The bottom number is always the number of protons or the atomic number. The top number is the mass number, which is the sum of the protons and neutrons. So remember, to get the neutrons, we subtract the two. To get the protons, we just look at the bottom number. All right, the bottom number identifies the symbol. That's what's super uber important. All right, so an alpha particle is basically a helium nucleus. That means it only has 2 protons and 2 neutrons and no electrons. So that means it's going to have a positive charge. That positive charge is very important. All right, the alpha particle is quite a large particle. It's a pretty big particle. Therefore, its strength is weak. It doesn't go through lots of things. It's going to get stopped. Think of like the air particles as like a strainer. All right, the bigger the particle is, the less likely it's going to get through the holes in the strainer. So an alpha particle, because it's such a big thing, its strength is weak. It's stopped by very small things like a piece of paper, a couple feet of air. A beta particle has the beta symbol or the beta letter. All right, and they can put the -1 up on here. All right, or they write it as 0, -1 E, or you can write it as 0, -1 beta. All right, basically a beta particle is a high-speed electron. All right, and if it is acting as a beta particle, it is a fairly small particle, so therefore it can get through lots of things. All right, this -1 number, the word that comes from is a beta particle is formed from the disintegration of a neutron into a proton and a beta particle. We don't go into that, but it does have a negative number, -1 atomic number, so to speak. And it'll make sense when we get into some equations that we're going to do. All right, a positron is basically a positive electron. I know we don't know what a positive electron is. All right, but it's similar in mass. It's got 0 mass, and that's the important thing. All right, and it's got a +1 charge. All right, it's the exact same thing as a beta particle, just the opposite charge. So that's why its penetration or its strength is medium. All right, and then gamma rays, you might have heard of gamma rays from, I think Marvels talk about gammas. I think the Hulk formed by the gamma rays, I think, maybe. All right, gamma is not even a particle. Gamma, it has no mass. All right, it has no mass and has no charge. It has no atomic number at all. All right, because it's such a small particle and it's just energy, it is very strong in its strength. All right, think of it like an X-ray. It can go through lots of things. All right, so that's kind of the order of alpha, beta, gamma. That's kind of the order of strength. Kind of remember it that way. This is the table that's on your reference tables. All right, and you're going to need this or be able to refer to this many times. We just talked about alpha, beta, and gammas. All right, and positrons. All right, they do put the neutron particle on there and they do put a proton on here. So they do put all the particles on here. And the thing that we're going to be concerned with in this unit are the numbers. All right, because we're going to actually use these numbers to figure out missing particles and such. All right, this is the simplistic symbol for them. All right, neutrons, lowercase n, p, protons, lowercase p. All right, you got your beta positive, beta negative, beta positive, and your alpha symbol. All right, what stops it? Like I said, alpha particles are stopped by a couple feet of air or a thin piece of paper, so it can get shielded pretty easily. Beta particle, a small or a thin piece of metal, a decent sized piece of wood will stop it. And then gamma, you're going to need, this is a couple feet of lead to stop a gamma particle. All right, so it goes through lots more things because of the fact that it's such a small particle. It's not even a particle, shouldn't say particle. Such a small thing that it's just energy. Okay, so neutrons, we saw this already. I'm just going to skip right over this pretty quickly, just refresh because people tend to write things down that they put on here. So neutrons have no protons, that's why it's a 0, and they have a mass of 1. A positron, which is a positive electron, is 0 + 1 E. And then a proton, it can be called a hydrogen 1 nucleus. All right, a proton is 1, has a proton number of 1, a mass number of 1, and symbol of H. Okay? All right, so here we go. So we're going to talk about alpha emitters and beta emitters today, and then we're going to be done. So if you're told that something is an alpha emitter, so radium 226 over 88. That means it gives off an alpha particle. So what I want you to do, so this arrow is the cutoff. So we think of it in chemistry as like an equal sign. You're going to write down an alpha particle. All right. So I chose to type in 4/2 alpha. You can do 4/2 He if you want. The numbers are important though. That's what's the important part. Now, having a periodic table, and unfortunately I can't pop a periodic table up here very easily. You're going to refer to a periodic table here. And what plus 2? So you're going to have some particle, some other daughter nucleus over here. That's what will come up on the next click. All right, but we're going to identify that daughter nucleus based on the numbers. Something plus 2 equals 88. So what plus 2 equals 88? So the missing particle is going to have an atomic number of 86. 86, if you look on your reference tables, it's got a symbol of Rn, which is radon. All right, so 86 plus 2 equals 88. That's how we figured out that there was 86. We figured out that it was Rn because of the number 86. You just looked on the periodic table. And then our mass number, what plus 4 equals 226. So 222 plus 4 equals 226. So all the sum of these numbers on top have to add up to all the sum of the numbers on the left. So the reactants and the product numbers have to equal. The reactant and product numbers of the atomic number have to equal as well. So in this case, radium decays into radon 222. All right. This is called the daughter nucleus. All right. They call the quote unquote offspring of these decays daughters. All right. It's just what they do. All right. Let's try another one. You should try this one on your own. All right. So you got uranium 238. Now notice I told you it was U, but I didn't give you the atomic number. So we look up the atomic number on your periodic table. The atomic number of U is 92. All right. I'm telling you that it's an alpha emitter, that it's giving off an alpha particle. So it's got to get off one of these. So 4/2 alpha. And then what I want you to predict or figure out is what is the daughter nucleus. So uranium, when you look up on your reference tables, is number 92. All right. I really wish I could write on this and still advance, but it doesn't let me. So 92 goes here. So we got to know what plus 4 equals 238. So the top number is going to be 234. That's step one. The bottom number, because uranium is 92, what plus 2 equals 92 is 90. All right. And then you look up on your reference tables, number 90's element symbol is TH. So you get 234 over 90 TH. TH is thorium. So the daughter nucleus, or uranium-238, would decay into thorium-234. Or the daughter nucleus of uranium-238 is thorium-234. Okay? All right. I'm trying to say it in lots of different ways, in the ways that we will see it. All right. So that's alpha emitters. All right. We're going to do beta emitters, and then we're going to be done for today. Beta emission. So we're going to take a uranium-239 isotope. Now notice if you look at uranium on your periodic table, it has a mass of 238. Remember that mass is an average. This is a specific isotope. So if they give you the mass, you have to use this mass. All right, 92 is always going to be associated with uranium. All right, it tells us it's a beta emitter. So that means it's going to be 0 over -1b. You can put it either if you want. So now what we want to do is we want to figure out what is the missing particle here. All right, what plus 0 equals 239? That's pretty easy. It's 239. All right, now here, because this is a -1, what plus a -1 equals 92? A lot of people jump at 91, but 91 plus a -1 is really 90. So we got to have a 93. All right. And when you look up on your periodic table, number 93's symbol is NP, which is neptunium. So uranium-239 will decay into neptunium-239. Or the daughter nucleus of uranium-239 is neptunium-239. Okay. Now, last one, you got P32. P32 is a beta emitter because that's what I'm saying it is. It's under this heading. So it's going to give off a 0 over -1b. All right. And then what particle is it going to produce, or daughter nucleus is it going to produce? 32 plus 0. So the mass is going to be 32. So that works out well. All right. -1. What plus a -1? Now P's number we didn't have down here. P is a 15. So what plus a -1 equals 15? So that's going to be a 16. So we look up on our periodic table. Atomic number 16 is S. So 32 over 16S. All right. And then that brings us into our next thing. So we are done for today.